Hi, good morning, everyone. This is Tuesday, June 25th, and another session of our course, Earthquake Engineering in the University of Victoria, Civil Engineering. I am seeing that we are building the momentum here. Hopefully you are hearing me. I'm using this headset today because there is some construction going on, some noise. This headset has a good noise cancellation. Hopefully you are not affected by the slightly more noise around me right now. A very slight, but I'm trying to cancel that for you guys. And yeah, looks like everything is working fine. People are joining us up to 16. Yeah, again, yeah, whenever you have question, typing is the better choice, and you can also write in the chat window. So let's close this as well. For now, minimize it. Make this smaller. Yeah. This is again course outline, and we are in the middle of module number 6. So we are talking about NBCC. Probably in terms of module, this module is the most important module of this course. If I wanted to like create a simpler course, I would have stayed with module number 6, some module 1 and 2, some module number 6 and 7, and the simpler version of 8 and 9. So that would have been a more simple level of this course. You guys are entertaining a more sophisticated one, probably comparing to most of other universities, but it's good. I mean, you will gain good high level knowledge of everything, and then anybody based on work or future education or research or work, you need more experience or more knowledge, you will dig further. But I think the slideshows that you are receiving, I edited them a lot last year. They are very good source. They have become very good source. I inherited good slideshows and I edited them quite a bit. They are now very good. Even myself, I keep them as my point of reference for a lot of topics when discussion arises. So that's the way we keep this course at high level, lots of, I don't call it superficial, good depth of knowledge on quite a few topics, however, not too deep. And mostly intended for structural earthquake engineers in comparison with like geotechnical earthquake engineers. Their area of focus is different. They are a lot focused on this topic of response evaluation and understanding the soil layers and how they basically change the characteristics of the earthquake. And also a very important topic for special structures or buildings is liquefaction that they study a lot. We do less for a lot of regular buildings. Yeah, as I said, try to avoid it, run away from it, or give it to your geotechnical engineer when the quality of soil is low and it's liquefiable, etc. And here we are, as I said, June 25th, the start of this week. Slightly behind, but yeah, we will catch up. We will catch up. Right now, it's the more important topic for this course, and I've tried to do it slowly or even redo and recap, etc., so that the people who spend time in the class learn slightly better. And the end of this week, that's very important, your deadline for your draft report. Not sure if the link is there. I will double check with Behnam and Armando so that there is a link for some sort of Dropbox where you upload your reports by end of day Friday, and then you can start enjoying your holiday. And yeah, I know that you have a reading break next week as well, so you will have a few days off studying and enjoying, or either one. Let's see where we left off last time, and we continue from there. I'm pretty sure that if the voice quality is not great, you will let me know, but I think it's okay. And this headset is a good one, so it picks up my voice and not much from the surrounding noise. We started this part, design spectral acceleration, last time, and we continue about the same place. And we started with the concepts or physical concept or physical phenomena behind the concept of site designation or site class. In most of engineering or in different codes, we normally talk about site class, site designation, and some new concept. I think maybe the other reason to differentiate between the two. However, traditionally or for many years, we talk about site class, which is important to us. Site class is a function of the type of material and the depth. We previously discussed site response slightly a couple of times, and we mentioned that the type of soil at location can sometimes even drastically change the earthquake characteristics. Therefore, it's very important to be aware of the soil material at the location. And in most, the important depth is 100 feet or 30 meters. And even in the US code, we call it VS30, although their unit of length is normally feet. But VS30 means like it's a measure of characteristics, which is the shear wave velocity at the top 30 meters. And you will see that a lot in the geotechnical reports that you receive for different sites. The most physical number that they talk about is in terms of the shear wave velocity at the top 30 meters. Now, site class or site designation per the new code. Again, we talked about the shear wave velocity at the top 30 meter. And it's the velocity in that top layers, like here, like we only showed 0 to 40. So that's the top 40 feet. And another 60 feet underneath is important for us. However, the indication is that the rest is all uniform, homogeneous, almost homogeneous bedrock. So 40 feet of like 2 soil layers and another 60 feet of bedrock here consists of a top 30 meter, which is important in site class and site designation. And yeah, seismic measurements in boreholes is like one way to get the like shear wave velocity using boreholes. That's a technique that still is being used a lot. However, now because good measurements that could be done on surface wave velocity in a way, ambient wave, which is caused by very small vibrations or daily super small earthquakes, because we can do good measurements of those, and some companies are expert in that. They can do it at less cost without having borehole or test. and therefore they can do more and better, which is good news, to characterize the soil and rock underneath our building. We are structural engineers. We are interested in the building, but I think we are in charge of the underneath as well. So we should make sure the geotech does a good job and provides a good report. Again, the relation between the shear wave velocity that I mentioned. Today, everybody is slightly late. Maybe there was some function in the university. Yeah, so the shear wave velocity and how it correlates with site designation. I'm less interested in that. I have not fully grasped why we need a site designation, but just for your knowledge, what we were in a way raised with has been site class in US, in Canada, overseas. So there's a lot of discussion about site class, almost same notation, A, B, C, D, E, F. And so for me, the most important is how it correlates with velocities, the shear wave velocities. However, when you obtain a geotechnical report, maybe the site classification is correlated with NPT test that they do, or the shear capacity of soil underneath, etc. A lot of dams, or the geotechnical report that I see for dams, they report to us the shear wave velocity, and they are correlated with each other. Now going to design a spectrum. That is very important plot or diagram that the code provides to you. We know that we discussed about the spectral accelerations as a result of any earthquake. However, the primarily method of analysis and design has been in codes for many years, that the code provides recommended design spectrum, which means the spectrum they recommend we use for the design. And it used to be like reading the design spectrum from some tables and maps in the National Building Code of Canada or ASTE 7. Nowadays, maybe they still publish those maps, but we are all lazy and we just jump onto the internet and try to read it from their website, their corresponding websites. And so it has been many years that they do that. However, something that I appreciated in basically the new website that we will look at is that the website also accepts the site designation as an input. So previously they got it for some site, I think maybe US or Canada, they give it for site class C or site class D, and then you had to do some manipulation to multiplying by some factors to get it for your site class, which was prone to some mistakes. Sometimes the structural engineer is not really too interested in that calculation, and then they make a mistake. So it was very easy to include that in their own calculator. And I quickly looked at the website and I realized that now it's in their calculator, which was a smart idea, I think, because it's not a sophisticated calculation, like multiplying by different numbers based on different tables that are a factor of a function of site designation or site class. But because it's not everyday job, every one of us would have made some mistake or misremembering how to do it or miscalculated, etc. Now the website does it for us. The latest website for 2020 National Building Code of Canada seismic hazard. I bookmarked the location here when you want to see the spectral accelerations we can click on it. Yeah, still valid from last year. I mean, that's 2020. And yeah, last year I created this slideshow. There was some students said that in BC 2015 was still valid last year, but I'm confident that now it's legislated. 2020 National Building Code of Canada is now legislated in British Columbia, and we must follow 2020 procedure, which is, I think it's easier to follow, or at least in this part, it's easier because it has accounted for site class for us. So this is the website. Let's see if we can figure this out. The code still allows, no, maybe there's a different website. I'm pretty sure that if there is a different web address that you can still use NBC 2015 or even earlier, because sometimes it's necessary. But when you go to this address, it's focused on 2020. So you have only one choice here, 2020. Okay. Here you say for site designation, looks like site designation is considered a higher level term. Do you want to use the, is everybody in? Nobody's waiting, okay. Do you want to use shear wave velocity at the top 30 meter? Do you have a value for that? Or you want to go with site class? Maybe I'm considered traditional. I'm more a site class person. Let's go to site class. And I think we just looked at that. Maybe if I go to the slideshow, this one, a few slides back. Yeah, site class, comparing with description. So yeah, we are going to build a building on good soil, stiff soil, so site class D. Let's go here. I want site class D, I like it. Address, yeah, so how do we want to give the address? Say my current location. Estimate my current location. Yeah, so I'm in the HDR office in West Georgia Street in downtown Vancouver. So almost or exactly, yeah, showing the location. That's where HDR office is in Vancouver. We have office in Victoria as well. And I encourage you guys to consider it for your job if you are looking for jobs. Now, so HDR is a good company. The presence of HDR in British Columbia was mostly architectural for quite a few years, but now they are hiring more and more engineers like myself, and there's interest in, like even the architectural department has interest in, say, timber design or building structural engineers. But I work on dams and hydro, which is completely different field. Okay, so yeah, so it looks like it can, like the new design of the site can even obtain the location using the GPS. Let's see if we see some valuable, reasonable numbers here. So again, it's summarizing that it's using the National Building Code of Canada version 2020, site class we said D, apparently it shows it as XD. It found my latitude and longitude, which looks okay, slightly above the border with the US. And yeah, so it describes it. So NBCC 2020, 5% damped, re-emphasized. So the values they produce is for 5% damped, spectral acceleration for different T's, where T is the period, and X is the designation. That's a new terminology, but now we are site class D is also designation. Also, it gives you the peak ground acceleration. The unit is gravity, so it's basically calibrated with G. It's unitless in a way because it's calibrated with G. And it also provides peak ground velocity in meters per second. Probability is expressed in terms of percent exceedance in 50 years. Further information on the calculation of seismic hazard is in background information. That could have been a good research or project for you to look at that background information and learn from it. 2% in 50 years, sometimes we somehow naively call it 2,500, or people who do better calculation, they call it 2475 year. That's what is important in National Building Code of Canada, and most codes around the world for building, everyday building design. However, they also provide 5% in 50 year, which is about 1,000 year return period, or 975. 10% in 50 year, which is about 500 return period, or 475. Are provided for additional information in accordance with this article of National Building Code of Canada. See the additional values tab for additional seismic hazard values for other designation periods and probabilities. So again, I'm very happy that this already does the site class for you. Otherwise, it was a calculation that we all do and we always make a mistake in it. So that's better that they do it for us. So at the location that I'm standing, so this column, sorry, I'm jumping to the right, peak ground acceleration is about 0.5 G. That's sometimes a good number for conversation. What is the peak ground acceleration at your location or at this building location? So it looks like downtown Vancouver, if the soil quality is good, would be half G, peak acceleration. Then what if you have a building with a period of 0.2? That building will see an acceleration more than 1 G. Wow. So you see that like the spectral response is more than the ground acceleration. So on the ground, you will see like 0.5. But if you have, say, almost a 2-story building with period of 0.2, you might experience, like at the floor levels, over 1 G in this region. And so what if your period is 0.5? What is this 1? I am in a like tall building. We already forgot how many floors are in there here, maybe about 20 to 30. So my period is about 2 seconds, and the maximum acceleration that I'm experiencing, I may experience during earthquake, is half a G. So that's the information that you get based on the primary period of your structure. And there are other information that the website is providing, but this table is the most valuable. So let's get back to our slideshow. That I love it that we are not required to do the calculations for site, but be aware that we accounted for the site already, like the internal calculator did it for us. Basically, so we finished this. We know how the seismic hazard tool works. And now that we read those values, now we should know what is the design spectral acceleration for a building. If the period is less than 0.2, like if you have a 1-story building, use the maximum between the value you are reading. The code wants to make it conservative. We may explain this later on, but we don't worry right now. We just obey or follow whatever the code tell us. Use the maximum value between 0.2 and 0.5. So let's see what did we have for my location. For my location, they're almost comparable, they're almost identical. Very, very slight 5% increase to 0.5. So the code was telling us to use, like for values smaller than 0.2, just use this value, the higher value, 1.16 G. And then for the rest, what you read is what you use. So only, yeah, remember this, for very like small period, remember it means a stiff, high stiffness. So for very stiff buildings, such as short buildings, use the maximum between what you read for 0.2 and what you read for 0.5 seconds, period. Okay, now that we have that, we jump to another important factor, which is importance factor. This factor, we have repeatedly looked at this equation. We tried to figure out RD and RO. We had a discussion about that. We almost figured out STA, which we obtained it using that website that I just showed to you, that calculator. And MV, maybe we will discuss further later on. Weight, we will give a few comments soon. Importance factor. The importance factor is put in there so that when, on one hand, I mean, like when there is a structure with low importance, you use a smaller load, like you reduce the shear, base shear. And when you have a structure with high importance or post-disaster, you increase the factor, like you increase the base shear accordingly. And this is for ultimate limited state, ULS. In Canada, we call it ULS. In US, we call it LRFD, which is basically both of them are the same thing. They mean you apply load factors for loads and you also reduce the capacity. So that's ultimate limited state. And remember that we had a quick discussion on different limited states. So for ultimate limited states, we use these factors, serviceability, which means deflection, mostly look at the section and deflections in the earthquake design. So you don't, I mean, different codes do it differently. Practically for deflection, we don't need an additional factor. Some codes, so remember that we don't need any factor for deflection, but some codes multiply and then divide, but some codes they don't even use it. So I already forgot what 2020 says, but end of the day, don't use any factor for deflections. Deflections should be as estimated by the like the real shear, not because we overvalue the shear, the loads, so that our hospital is super spry. But when we want to assess the deflection, it's like the real deflection in a way. But I think we will discuss the deflection as well. Yeah, I think you can use this. However, we didn't tell you, I didn't tell you what these categories are defined. It's in the next slide. It's basically importance categories in buildings. It is used for different loads, maybe even for snow or wind, which I'm not good in either one. Therefore, it's not part of the definition is not part of the earthquake. So, but it's like in a table. And remember that we said this section 4 is about loading. So it's important to us as structural engineers. And everything 4.1.8 is earthquake, which is important in this course, this current course of yours. But this is 4.12, maybe teach on some general notes and concepts, such as importance factor. Normally, we should start with normal. What do we mean by normal? A normal importance category building is a building that does not meet the criteria for low, high, or post-disaster. Okay, I completely said the reverse. So first, let's define the abnormal, and then everything else is normal, such as the buildings that we are in. What is abnormal? Low importance. A low importance category building is a building that represents low direct or indirect hazard to human life, such as maybe some non-residential farm building where they keep the hay or wheat or etc. So people will not be hurt if that building slightly collapses. So those could be low category where humans don't stay much or don't live or stay or work just for storage. They can be low. On the other hand, what is high? A high importance category building is a building that provides a greater degree of safety to human lives. Community center, elementary, middle, and secondary school or higher are high important category buildings. Yeah, not sure if BC also supports this. So sorry guys, but colleges are not high importance. So colleges are regular. The society tries to protect people until the end of secondary school. Maybe in the city of Victoria says also colleges are high importance. So this is also affected by local regulations. Post-disaster building is, or a structure for us, it says building, but really a structure is everything that we think should survive a major earthquake, like really remain functional, operational after earthquake, like a major bridge. If the bridges are cut, then we cannot really bring in food for people. Like at least say, city of Vancouver is surrounded by bridges. And if after an earthquake, those bridges are broken, I cannot say that it's very disastrous to people. I mean, there are some cars on it, but after post-disaster is important because then they cannot freight food into Vancouver and Burnaby and the cities in the middle. So a lot of major bridges are post-disaster. Dams are, I consider, post-disaster, although we don't really exactly follow NBCC, but if I want to make equivalence, I would say it's equivalent to what NBCC consider post-disaster. We want fresh water, electricity, and also if a dam breaks, a lot of communities will be flooded and they will be in danger. And then if there's like toxic material in a building, that's definitely post-disaster. You don't want it to break and release the toxicity. So you get the idea here, how we have different categories. We reduce the earthquake for low, and we increase it for high and post-disaster. But in category, yeah, we pay attention that maybe local regulations override. Like I have quoted NBCC, but you guys at least should look at BC Building Code. I don't think so, but it's possible. It's not impossible that they have override this. Maybe a city, like the most local one is the most important. Maybe city of, say, Victoria says that college is also high importance. But as far as the National Building Code was concerned, they went as high as high school. Okay. So let's move on. Weight. Yeah, so weight appears to be, or we think that it's trivial, just add every weight in the building, W. But the code has some description. A specified dead load. So the dead load is the most important part of it. Normally we say maybe only dead load for a lot of calculations. So what you previously learned to be dead load in the building code, except that the minimum partition weight need not exceed 0.5 kilopascal. So don't include every partition weight, just up to 0.5 kilopascal plus 25% of the specified snow load. This is plus dead load. So include dead load, include 25% of the snow load. And 60% of the storage load. So we are seeking more like more permanent loads that they may really experience earthquake. Here, like snow, I mean, we are not in a snow region, but even in the snowiest regions, they don't have, in a way, permanent snow. So on an earthquake day, they have estimated that maybe 25% of that snow load is valid. And in Vancouver or Victoria is less of a concern. A storage load appears to be almost permanent, although it might not be categorized as dead load, but it's almost permanent. So I tried to give a good estimate of what loads in the building will really experience that earthquake, which is like, what was it, like 2,500? So 2% probability every 50 years. 50 years is like maybe the expected life of a building or a structure. We always assume, the society assumes that like a building should at least survive 50 years, and then we want 2% chance of it. Like even if an earthquake with 2% chance happens, we want to protect that building against that earthquake to be uniform. And description of the dead load, a specified dead load for structural members, weight of self-weight of the members, construction incorporated into the building, which are permanent, partitions. However, I think we had a like limit for partition up to 0.5, permanent equipment, and vertical load if the soil is sitting on your structure. Some bridges have soil on them. Nowadays, some buildings have soil on top with some trees. So don't forget those. So in earthquake weight, by W, we mean the weight of everything that we think is permanent. Again, end of this slideshow. Let me know if there are questions. And then I can jump into the next one. Okay. Not much concern here. Close it for now. So another re-emphasizing the equivalent static force procedure, which is very important procedure for your analysis and design. And yeah, asking for questions. Let's continue. That's basically continuation of the same module. We want to discuss the load path one more time. We said that load paths are important, and a lot of times we say the top, in a way, top responsibility of a structural engineer is to provide load path and ensure that load paths are there. Like for any load that may happen in that region, or any load that we know of, there should be a load path that carries that load to the foundation. That's what we should be aware of, and we should really, a good structural engineer should be really target or plan to address all the load paths. Load path for seismic in a building structure. The seismic weight must be transferred to the foundation through a viable load path. The seismic load, well, maybe it's a seismic weight. I will edit this. So the lateral seismic load, we should think ahead. We should know how that load transfers all the way to foundation and dissipates. This must be considered both in a horizontal plan and in vertical plan. So vertical is mostly weight or vertical earthquake, which is becoming more important. And horizontal means lateral loads caused by the earthquake. They should go to the foundation. The building code has consideration for irregularities with respect to how the load travels to foundation. So the code is normally more stringent when there are irregularities. Regularity means that, I mean, our life is comfortable as a structural engineers if everything looks regular, meaning there is small change vertically, every plan is almost the same, small change in, say, elevation, where like all the sections of the structure look the same. And that's why, I mean, you see that most of the buildings, even high rises around us, are cubical because they really meet that requirement and make the life of structural engineers easier. When there is more and more irregularities, the code doesn't say don't do this, but it says like you need more sophisticated calculations or think ahead about your load path. Yeah, we keep on talking about seismic force resisting system, SFRS, is part of the structure which is intended to resist the seismic load. So load path was about how the loads get to foundation. SFRS is about how the earthquake load gets to the foundation. It must be designed to take 100% of the seismic load and act to protect the gravity system. So here you have the bracing, which was maybe naturally you think about bracing the structure. It transfers the lateral load all the way to foundation through bracing, and it keeps the vertical load carrying system in place. So therefore, like what the concept of collapse that we can think about is that after an earthquake, the lateral force resisting system, the seismic force resisting system didn't acted properly. Therefore, the vertical load resisting system damaged and the structure collapsed under the self-weight. So basically, SFRS is actually protecting protecting the vertical load carrying system as well. Seismic force resisting system, again, typical braces for you. In the National Building Code of Canada design philosophy, the vertical or gravity load system cannot be used to resist lateral loads. So have it in mind that you really should design your lateral load resisting system separately. However, it practically takes some lateral load, and the vertical system will need to move. I mean, say to activate these braces, everything should move slightly so that these braces are elongated and they start to resist the lateral load. And the vertical system may experience pass-through seismic loads that are larger than gravity loads and must be considered in the connection design. So basically, connection designs should also consider the lateral load, which we will discuss that as well. Different types of seismic force resisting system. The primary concepts in providing seismic resistance is through moment frame. So this frame has moment resisting connections at each floor. Therefore, if you force it to move laterally, every beam and column will bend and resist deformation. And in a way, they resist the earthquake. Brace frame, something that's easily everybody thinks about bracing. I have a lateral force, what should I do? Let's brace it. Typical bracing, which is mostly for steel frames or maybe even mixed design. Moment is definitely both steel and concrete, or wood, maybe less of a wood, I would think. And braced, you mostly think of a steel that is braced. Shear walls, like putting a wall here with resist the lateral force, could be either one. Shear wall primarily reminds me of concrete shear walls, but wood shear walls are also used a lot. And one that I haven't used, but I mean, it's being used is steel plates as shear wall. That's also doable. So different important types of seismic force resisting system in here. Focus on shear wall. So here we are comparing the shear wall system, which resists the earthquake, or a modification in it where there are some openings as door in it. It's called coupled wall, but the same concept. So the shear wall is resisting the lateral force. This is the one that I said I have not practically seen, but it's used using plates at the location of the shear walls in a building and to provide resistance. So it's, yeah, I mean, theoretically it's doable, but practically, even in still high rises, we have like the elevator shaft, which is practically concrete shear wall, but this is also doable. For masonry, you can only think about shear wall effect, using a wall to resist the shear force. For wood, also shear wall should be popular because you can put a panel in there, wood panel, to resist the shear force or lateral force. So brace frame systems. Brace frame systems could be concentric or eccentric. Concentric means that these two braces are almost meeting at one location. So this is like a chevron type, but they are concentric. They are meeting each other at one location. And these ones are eccentric, means that there is a distance, a shear panel in a way, where they don't really meet each other on the structure. So they are separate from each other. They are eccentric. And we will see that this one provides slightly better ductility to the structure, but which means that more detailing is required and more careful detailing is required with this one. But then you gain a higher reduction factor. So your earthquake load would be smaller because of the ductility that is provided. This one could be designed or constructed in more traditional way, and it provides ductility, but less ductility. Moment resisting frame, again, yeah, emphasizing that there are rigid connections between beams and columns so that they can take moments and the structure doesn't really collapse under lateral force, but it shows resistance. And this also shows a lot of ductility if properly detailed. However, like this design results in more deflection. So the deflections would be larger and providing serviceability might be slightly more challenging. Earthquake forces in shear wall systems. The force is applied here. At the base, you see the highest shear, and you see a moment that you should design for. And that's a typical concrete shear wall or reinforced concrete shear wall design. If you have a coupled wall with some openings, maybe that moment, most of this moment will be interpreted as tension on one side and compression on the other side. But each one of these smaller shear walls also see their own moments. So it should be designed accordingly. Also the shear at this narrow pseudo beams would go high because these two, like the left portion and the right portion, in a way they are interacting with each other through shear in the middle. And there would be a lot of shear force or a bigger than usual shear force in these short beams. Steel plate is almost the same thing as reinforced concrete shear wall. It creates moments and shear at the base, which should be designed for, or if there is like fewer plates at the base, then the moment will be interpreted as tension on one side and compression on the other side that should be designed for. How the earthquake force transfers in brace frame systems. If it's concentric, basically, say a lot of the load transfer is through the braces. Part of it would be through the columns, which means that the columns will see compression and tension, but most of it is through bracing. One of the braces is in tension, the other one is in compression. So they should be designed accordingly. However, if you have eccentric bracing, where these two braces are separate, there is an additional phenomena and at this separation where you see a lot of shear force and the shear yielding happens here basically, which is a good source of ductility. That's why the eccentric brace frames are considered more ductile because of this shear yielding in this area in between, which dissipates a lot of energy. Moment resisting frame, how the forces are built in there. Only because of the lateral force, every beam is seeing shear and moment at the ends. And also every column is seeing a shear and moment. And based on like which side, one side it sees a lot of tension, the other side is seeing a lot of compression, but then the earthquake load reverses. So both sides are designed for tension and compression. That's the load transfer mechanism in moment resisting frame. Now the equivalent static force procedure. It is common to do design based on dynamic analysis, either by response spectrum, time history, or nonlinear analysis. That's some engineering judgment that probably we need at least response spectrum. However, in some cases, or a lot of cases, we can use equivalent static force procedure, ESFP, which is the big thing that the code gives us when the structure is considered more regular. The code gives us equations on how to distribute the lateral force to the structure, the base shear that we already calculated. And it is important to understand its process and limitations. So the limitations are important when we hit the limitation in an irregular structure, unusual structure. We should go back to, say, common sense and use dynamic analysis, because it's a dynamic phenomena and we are simplifying it by a static equivalent procedure. And therefore we should know when we can basically use that simplification. Yeah, again, remember that we already calculated the base shear, which is this V. We almost find out all the parameters in there. Maybe the higher mode effects we didn't discuss yet, but that's because it's really related to taller buildings and it will come up now. And basically what the code tells us is that we calculate some weight functions, W's, and we take advantage of the height of each location to distribute the load between the basically at different elevations. So the distribution is based on, say, weight, like we want to know what is Fx. And for a moment, forget about Ft. So you have your V, you have your base shear, and you want to distribute it, and you want to know what is at this floor, which is floor number X, appears to be floor number 3. And so the code varies this, or different code makes some variations of this, but the most important concept, which keeps on repeating in different codes and different versions of same code, is weight of the floor multiplied by the height of the floor from base. And then divided by the summation, repeating the same thing for all floors. So you do the same for first floor, second, third, fourth, and fifth. And then you create basically this multiplier that gives you the force at third floor. And then some of the codes like recommend using, in a way, nonlinear distribution, when, especially when the height is, like when you have a high rise. This code, the National Building Code of Canada, instead of making it nonlinear, it keeps it quite linear, like a triangular, but it adds additional load on top, which is Ft, and portion of the V to be concentrated at the top of the structure. This is 7% of the TA multiplied by V. So basically, in order not to double count it, you reduce it from total, you distribute V minus Ft between all floors in a triangular fashion based on this equation. And then you apply the additional Ft on top. Now we go back to that factor that we didn't describe more, higher mode effects factor, MV. The actual response of a building is sum of multiple modes. MV accounts for higher mode effects because the simplified solution base shear equation that we looked at is mostly based on one mode effect, but we want to indirectly account for higher modes. This higher mode factor is a function of the type of building in a way, fundamental lateral period of the structure, and the shape of the design response spectrum. Higher mode effects are greater for long period wall systems. Tall wall systems have more higher mode effects. And we don't consider higher mode effects if our primary period is less than 0.5 seconds. Because when you have a shorter structure, about 5-story building with TA less than 0.5, then there is not much higher mode effects. So the higher mode effect, what is the factor J? J is base overturning moment reduction factor. We reduce the overturning moment based on J, and it is required because when MV increases, the base shear to account for higher mode effects. The shear, we want to increase it, but we don't want it to cause overestimation of the base overturning moment. The reduction factor is applied at every level of the structure, except for the top 40% of the height. So we don't really apply it to the top 40%. Base 60% we apply. So naively, or based on, say, your hand calculation, you expect the moment at the base, which will cause tension and compression at the base, to be summation of forces multiplied by the corresponding height. But this is overestimate, so we reduce it for the lower 60% of the height based on this equation. J plus 1 minus J multiplied by Hx over 60% of the height. So it reaches the maximum at 60% of the height, and then you don't reduce anymore over the 60% of the height. Those factors are, maybe I should reverse the order of this slide and firstly tell you that you read both MV and J from the code. So as you see here, for different ratios of S.2 over S5, the code recommends different increase factors for base shear. So the base shear mostly remains the same. There are some factors greater than 1. And then at the same time, the code doesn't want you to overestimate overturning. Then it recommends reduction factors for the same situation or condition. So this is based on this ratio and the period of the structure that you either calculate or estimate using the code. So basically, yeah, so the steps is that you first go to the code. If I want to be prescriptive, go to the code and you know your structure, you know the spectral accelerations that you read from the website, you know about this value, and you know about the period of your structure. You read the increase factor, if anything, for different structural types from the code, and the reduction factor for moment from the code. Then you take one step backward apply that, calculate the reduction factor for each floor, because the reduction factor for each floor is different, and reduce the overturning moment that you are designing for based on the factor. That's for overturning. And for base shear, the total value of base shear, you use MV, and then you apply the increase factor to your base shear. Yeah, I have shown you the equation for base shear a few times. Progressing further. The equivalent static force procedure may be used for structures that meet any of the following criteria. The seismic category should be seismic category 1 or 2. So that simplified solution, how we distribute the load in height, which is by a couple of equations, has limitations. It's only applicable in seismic category 1 or 2. And the structure should be regular, meaning that I will discuss what regular means, but the structure should be less than 60 meters in height. And the period in this direction and in the other direction perpendicular to it should be less than 2 seconds, indicate about 20-story building plus minus. And structures, if the structure is with irregularity, these types of irregularity are acceptable, but the height could be a lot less, only 20 meters. And the acceptable period is also less. So you should go through this, or we go through this more than one time, because like sometimes one slide or one concept depends on the next concept. What is seismic category of a building? This is like similar ideas of seismic category has been in US building code for quite a few years, but I think it is introduced to National Building Code of Canada only in 2020. 4 seismic categories. And there are 2 categories, one based on the spectral acceleration at shorter period, one based on the spectral acceleration at the longer period that we read from the website. So based on this value, you come up with one seismic category. Based on this value, you come up with another seismic category. And this note says the more severe of the 2 is considered the seismic category of the building. So you basically look at 2 criteria and decide about the seismic category, and the larger seismic category, which means more severe, is the seismic category of your building. Based on the importance factor multiplied by the spectral acceleration at short period, and importance factor multiplied by spectral acceleration at a long period, which is 1 second. So 1 second versus 2 seconds. And okay, sorry, it looks like I missed one question, hopefully not a long time ago. How to keep the moment from taking the gravity load 11, okay, not a long time ago. Moment, yeah, please open your mic, because I'm not seeing everything, but let's see what was related to. How to keep the moment frame from taking gravity load? There are usually the main beam and columns. Yeah, I know what you are talking about. I think I can guess because the code emphasizes that keep your vertical design separate from your lateral design. And then, yeah, then any engineer says, okay, I have a moment resisting frame. They are the same. I think the code means conceptually keep them separate, like design that frame for your vertical load and seismic load, and the combination of the two. Normally we use the load combination. So I see it as more conceptual, especially in the moment resisting frame. Yeah, that's interpretation of that statement is a little bit, yeah, it might cause confusion that do I need two moment frames, one for vertical and one for lateral? No, practically that's not the case. That same moment resisting frame does both jobs, and in a way we combine the loads. So that system has some separate capacity. Maybe we can think about that in terms of capacity. That frame has 50% capacity for gravity and 50% capacity for seismic. Pretty much the code says don't use the same capacity for both purposes in a way, and the building should be doing both tasks at the same time. Yeah, so sorry for the confusion. Yeah, sometimes the code talks more like a legal document rather than engineering document. Yeah, so seismic category, as I said, is new to Canadian code. Two separate criteria. One, and this, choose the higher number. Now irregularities. Yeah, that's why I think in this portion, I'm right to repeat some slideshows a second time because, or have a recap, because sometimes we talk about something before even introducing it. So I will do the same thing even on Friday. We will have some recap so that because you have advanced further, now you can see some of the definitions. What is a structural irregularities? So the irregularities are in NBCC, and what makes a structure irregular? When the stiffness of lateral stiffness of a structure mainly changes from one floor to next, or from one elevation view to another elevation view. When there is radical change in mass, like one floor is suddenly designed to be very heavy for equipment, while the floor above or below it are less massive. Load path or geometry, when the geometry suddenly changes in a building. Weak story effect, when a story is suddenly designed to be very weak, especially at the mid height of a high rise. Suddenly we have, I don't know what the reason could be. Maybe they need a lot of opening, and then suddenly they don't use braces. Then that story has become weak, and therefore irregular. Torsional, meaning that center of gravity and center of rigidity are not the same, which we have mentioned that previously, but we will emphasize it again. And when there is irregularity in a structure or high rise, there are height limits. I showed it in some previous slide. If you go back, maybe it makes more sense. Seismic categories, SC1, SC2, that's where we are allowed to use simplified solution. Only these two seismic categories that meet these requirements. And then if you are regular structure, then you can go quite high. And if you are irregular structure, then we will discuss what we mean by types of irregularity, but it's mostly around stiffness or mass irregularity in elevation or in plan. And then the limit on elevation is less, a lot less. And period means almost the same. Period and elevation have a correlation. So that's what we mean here. And then when the structure becomes very unusual and irregular, then we need dynamic analysis. Or it becomes important for important structures, post-seismic. I would recommend dynamic, such as our dams or major bridges. Now, yeah, we just want to high level show you the types. We talked about the types of irregularities. These are the numbering and more numbering here. That's what we will discuss next time, which is based on stiffness issues, mass issues, horizontal and vertical issues, and changing geometry. Just gives you a heads up on what will come up next time. We have, I think, a good location to stop this, hoping that everyone is going to have good rest of the week. Stay focused on your report submittal. It's very good timing before you rest in a long weekend and reading break. You don't need much reading for us because you already has catch up by Friday. By Friday, you submit your draft report and you feel good about this course. You don't need to do much reading, and you will be enjoying the long weekend. Therefore, stay tight until end of Friday and finish your task. Anyways, I'm waiting for questions. Yeah, you guys are free to go. But if somebody has a question, I am here until 12:20, and then we close off. Thank you. Bye, everyone.